Hello, my name is Aina and George, and today I will present our paper, Efficient and Provable Local Capability Revocation using Uninitialized Capabilities. Capability machines are a kind of CPU with support for fine-grained privilege separation. And one such family of capability machines is CHERI from Cambridge University. Beyond being, products of research, capability machines are also becoming a reality in industry. So Arm recently started developing a CHERI extended processor called Morello, and one of the guiding design principles is security by design. So it's quite important that we know how to analyze and prove what kind of security properties we can actually get out of capability machines. Now, CHERI comes equipped with local capabilities, which are a kind of ephemeral capability, meant to grant only temporary privilege. So from a technical point of view, local capabilities can only be kept in registers and on the stack. And indeed, one of the important applications of local capabilities is for the stack itself. Another important application are for return capabilities, acting as the return pointers during function call. And these two applications must enforce two abstractions that exist in most high-level languages, namely well-bracketed control flow and local state encapsulation. And we expect these two abstractions to really be inherently stack-related. So we want our stack to act in a very specific way that should enforce these two abstractions. However, as we'll see in more detail, the challenge is to enforce these two abstractions efficiently. Namely, it unfortunately requires us to clear the full stack at every function call and return if we want a guarantee that these two abstractions hold. And this is, of course, quite undesirable. And it was explained in great detail in the paper by Skorsenbars and others. So this paper goes into great detail about why clearing is needed, and our work builds upon that paper, but with a new solution that does not require stack clearing. So we propose uninitialized capabilities, a new kind of capability which does not permit reading the unused part of the stack. This new kind of capability is our first contribution. So we propose uninitialized capability as a capability granting read-write access to memory without exposing the memory's initial content. We then explain how uninitialized capabilities redeem CHERI's local capability as an efficient revocation privative. We characterize these guarantees provided by uninitialized capability with a capability safety result as a universal contract that holds for arbitrary assembly programs. And we use a step-indexed Kripke logical relation defined in the Iris logic using Iris features like shared invariance, and our results are mechanized in the Coq implementation of Iris. We then define a new and efficient calling convention and provide evidence that it enforces well-bracketed control flow and local state encapsulation by proving an implementation of the awkward example correct. We implement uninitialized capabilities in the sale semantics of CHERI MIPS and the Clang LLVM assembler. For the remainder of this talk, I will first elaborate on the challenge of the efficient revocation of local capabilities. And to this purpose, I'll present a more technical detail, a simple capability machine, and I will motivate the need for revocation and discuss what revocation looks like in the presence of a stack. So this is all built on prior work from local capabilities in the CHERI group and the paper by Skorsenbars and others. Then next, I'll present uninitialized capabilities in detail together with the new calling convention. And finally, I'll give a high-level overview of how we actually model these uninitialized capabilities in Iris. But first, let's motivate the need for local capability revocation. And to do that, we will consider a simple scenario with two actors, Alice and Bob. Alice and Bob each have their own memory space, or heap, which are disjoint from one another. And in the first version of the scenario, Alice just calls Bob once, and she wants to share a pointer to her heap to Bob, pointing at address C. However, she wants to make sure that Bob does not gain access to the rest of her heap in the process. And for that purpose, she uses a capability machine. So a capability is really a concept which has different meanings at different levels of the machine, but they all share a common tagline as an unforgeable token of authority. And at the machine level, a capability is the token that grants access to memory. So the only way to access memory is through a capability which has authority over that memory. So the authority is defined first by a permission, such as read-only, read-execute, read-write, etc. It is then defined by range authority, here from address B to E. So what that means is that you can only use this particular capability to access addresses between those range. And since capabilities replace pointers, they must also point to any particular address, here A. Then the instructions of a capability machine dynamically check that the attempted load or store instruction is within the bounds of authority of the capability. For instance, a load instruction will dynamically check that the address A is within the range BE, and that the permission is at least read-only. If these conditions hold, the instruction executes. If not, the failure is flagged. And different things could feasibly happen at this point, and in our simple capability machine, will simply crash and end in a failed configuration. So let's go back to our scenario. Alice now hands Bob a read-write capability with authority only over C. And note that I'm being more precise here when saying that Alice hands Bob a capability by indicating that Alice hands over the capability through register R. And now with our capability machine language, we are in a pretty good position. Bob cannot use this capability to access the other addresses of Alice's heap. Good. However, let's make the scenario a bit more interesting. So Alice now wants to make 2 calls to Bob. And in the first call, Alice grants Bob privilege over C. However, in the second call, she does not. During the second call, Bob should not have access to C anymore. However, something will go wrong. So the capability is a word like any other and can be stored in memory. And Bob does exactly that. So during his first invocation, he stores the capability pointing to Alice's heap in his own heap. And Bob can now access C during the second call as well, which is not desirable. And this is where local capabilities come into play. So we want to make sure that Bob cannot store a copy of the capability onto his heap. So we augment capabilities with a bit. Now a capability is either local or global, where local indicates that it cannot be stored on the heap, disallowing Bob to store the capability. In this picture, local capabilities essentially become register only. The problem is this is unfortunately a bit too restrictive. So we need a mechanism to allow register spilling, where parameters are passed on the stack. In case Alice hands too many local capabilities to Bob, they need to be stored somewhere. And this is exactly what we'll use the stack for. So what's a stack in this picture? A stack will be a part of memory, which unlike the heap, can contain local capabilities. And we do this by extending the lattice of permissions with write local permission. So we get 2 new permissions, read write local to the left and read write local execute on top. And a capability with these permissions can be used to store local capabilities. So in particular, a stack is a capability with a write local permission. So let's go back to our scenario, but now with a stack. The stack is depicted on the left, and it has a read-write local permission. And crucially, it will be shared between Alice and Bob. So before the first call, Alice might use a part of the stack, and she will then hand out a restricted capability to Bob to protect her local stack frame. So with this capability, Bob cannot read Alice's local stack frame, but he can use it to store any word he wants. So in particular, although Bob cannot store the capability to C on his heap, he can store it on the stack. And the problem is, if Alice does not override Bob's stack frame before the second call, that word will still be there, and Bob can access the location C during the second call. So we're back to the undesirable situation. And in fact, the only solution here is that Alice must clear the full stack prior to the second call, because she has no idea in particular what Bob's stack frame is. He could have stored it anywhere on the stack. So she must clear the full stack prior to the second call such that Bob cannot access that capability again. And the downside is this is very costly. Obviously, clearing the full stack before each call is quite undesirable, and it's also excessive. If we are doing n calls, we'll be clearing the full stack n times. So we propose an alternative with uninitialized capabilities, and I'll now spend some time explaining what those are. So an uninitialized capability has a permission pi on the range BA, which we call the initialized part here in white, and then it has a write-only permission on the range AE, which we call the uninitialized part here in gray. And as addresses are written to, they essentially become initialized. So the boundary between the initialized and uninitialized part moves up. And what that really means concretely is that with this capability, we can only read from BA, and then we must override the previous content of AE before we're allowed to read it. So we can never read the gray part without first having overwritten it with something new. And we extend our lattice of permissions with uninitialized counterparts to the 4 writable permissions. And I will sometimes call them U counterparts or U permissions. So writable permissions can be restricted to their U counterpart. So for instance, a read-write permission can be restricted to a uninitialized read-write. Also, U capabilities can be restricted in parallel to their initialized versions. So for instance, uninitialized read-write local can be restricted to uninitialized read-write. And then we extend our capability machine language with 3 new operations meant to operate only on uninitialized capabilities. So those operations are load U, store U, and promote U. Load U takes a destination and source register and an offset, and then it checks dynamically that the address we are trying to read, that is A plus the offset, is below the current address A and between the range BE. So in this particular example, our offset is -1. So we need to check that A plus -1 is less than A, which holds, and also that the A -1 is between our range of authority. And if that holds, we are loading the word at the address A -1, which in this picture is W. So as a result, our destination register will be updated with W. Likewise, store U also takes a destination and source register and an offset. But now, since we are storing something in memory, we also need to check that if the word we are storing is local, the permission must be write local. So here I'm indicating pi, meaning the non-U part of the permission has to be write local. And in this case, I'm showing a particularly interesting case of store U, where the offset is 0. So if the offset is 0, we are additionally increasing the current address of the capability. So we're increasing the initialized part of our uninitialized capability. And the result of this instruction is to store W at A and then update the address of our destination capability to A plus 1. So we're increasing the initialized part of the capability. But of course, we overrode the word that was originally at A in the process. And finally, promote U just takes as input a capability, and it promotes a capability to its pi counterpart, its non-U counterpart. But it must do so for the initialized part only, since that's the part we are allowed to read. So as a result, we get a non-U capability with permission pi, but now with range BA. And this is sound because we can read exactly the same part that we could before. Now with these instructions, we are going to define our new calling convention. So first, at program startup, we make sure that there is a local stack capability with permission uninitialized read-write local execute. So this is the top permission in our permissions lattice, and we make sure there's uninitialized. Then, when called by an adversary, we dynamically check that the stack capability indeed is still uninitialized read-write local execute. Then, the part of the calling convention which will have the most difference and which will also be faster is when calling an adversary. So we do everything as the calling convention presented by Scoresling and others, but we do it without any stack querying. So all that is needed is to hand out a completely uninitialized capability to the adversary. And these drawings depict an example stack at the beginning of a function to the left, and the stack that is handed over to the adversary on the right. So note that we're handing an uninitialized capability with range AE currently pointing at A, so currently pointing at the bottom, which means there's no way to read any words from A to E unless they have been overwritten. And note that there's also no access to our local stack frame, BA. So BA here just represents our local stack frame. We will just keep that completely unreachable during the adversary call. So when returning to an adversary, so this is at the end of our function, we're jumping to some return pointer, we must still do a bit of clearing. So we cannot completely forego clearing. And the reason is that we don't want to leak any capabilities to our caller. So when returning to an adversary, we are clearing the part of the stack that we used. So in these drawings, that will represent our local stack frame, BA. And note that this stack clearing is still substantially smaller than previously. Our local stack frame is in practice much smaller than the full stack. We only need to clear it once we return, and there's no clearing at all when calling an adversary. So finally, I'll now give a high-level overview of how we actually model these uninitialized capabilities. So first, what is an idea of our approach? It's twofold. So we define a program logic to reason about known code. And then we defined a step index cryptological relation to reason about unknown code. And because of the dynamic checks of a capability machine, although there are no static guarantees from the program, we know that the capability machine language enforces some notion of capability safety because there are dynamic checks that can fail and stop you from doing something undesirable. And the logical relation is meant to capture exactly that notion. So we can see the logical relation as a universal contract guaranteed by the capability machine. And this universal contract is proved correct through the fundamental theorem of logical relations, which will say that all arbitrary programs adhere to the universal contract. And this full approach is mechanized in the COC implementation of Iris. And during this overview, I will sometime, take some steps aside and talk a bit about some of the specificities of the mechanization in Iris. But for more detail, I will refer to the paper, and those asides are meant more for an audience that already knows a bit about Iris. So we begin by defining a detailed operational semantics of our simple capability machine language, which goes from configuration to configuration. Now, configuration is the pair of the register state and memory states. And note that there is no expressions here in our operational semantics steps, and that's really because in a machine, everything is really just stateful. Programs lie in memory, programs are pointed to by the program counter, and our steps only really just change the state. Next, we define a program logic where we use points to predicates to reason locally about registers and memory states. So we are able to define Hort triples that really only talk about the footprint of an instruction. So in this, in our machine, we have the register points to, which just states that register R points to word W. And then we also have memory points to, which are additionally indexed by a permission, here P, which will limit the updates to the predicate to those allowed by that permission. So these really just reflect the updates that will happen by the capability machine. Now with those resources in place, we can define our Hort triples in our program logic, which will typically look like this. So the precondition has information about the program counter register and the address of the current instruction, A, and that instruction would in this case be W. And all instructions will typically, have this skeleton. We will always need to know the program counter and the address of the instruction. Then the expression in the middle is really just a flag that indicates that we are executing a single instruction. So it's a flag that lets us know what kind of execution we're in right now. Just lets us know how to interpret memory. And then in the postcondition, typically the program counter will increment by 1, and the remaining state or footprint of that instruction will update accordingly. So if we have a move instruction, the footprint would require the registers of the move, and in the postcondition, the word of those registers might change. And for known code, we just step through the program by applying these Hort triple rules for each instruction. So we just continue stepping through our single-step instructions and update the state accordingly. So of course, we can't really do that for unknown code. So for unknown code, we use a logical relation. And what we do is we define two relations, the value relation, which enforces that a capability only has safe authority, and the expression relation, which enforces that executing a capability does not exceed its given authority. Each relation is indexed by a word W, which associate the content of memory to invariance. So of course, a capability gives access to memory, So we have to have certain invariants about that memory, and this is what we use W for. The world has two parts. So first is a collection of invariants or predicates, which each depend on the state of the world itself. And these invariants must follow a standard protocol that is depicted below. Each predicate will be in some state of the standard protocol. So in this example, phi is in a frozen state, and they can only update according to the transitions of the standard protocol. And then, of course, the predicates themselves might depend on the current state they're in. So this part of the world will contain all of the invariants for the shared part of memory. And when I say shared, I mean, for example, Alice sharing a capability to Bob. And since we are sharing this capability, we can't really know much, what is going to happen to the state of memory, but we do know it has to adhere to the standard protocol. So that's the guarantee we get. So as soon as some capability is shared, we want to know that it follows and will always follow the standard protocol. However, if some piece of memory is owned, if it's never shared, its content does not need to follow any standard protocol. We will have full control of it, and it is only known code that will manipulate it. So if we can prove that it follows some completely custom state transition system, then we can use it. These invariants are independent from one another, and they are completely custom. So here, phi prime, has a current state in a completely arbitrary custom state transition system. Okay, so this is one of my one iris aside. So the slide is really meant for people that are already a bit familiar with iris. But I want to talk about, what is different about this logical relation mechanization. So before I saw how the world can be depicted on paper, but of course, this definition would be circular, and we would need to solve the world circularity problem by solving a recursive domain equation, and that's a whole can of worms. But in iris, we want to leverage iris features to define worlds without explicitly having to solve a recursive domain equation. So for the shared standard part, we do this by using iris's saved predicates, where instead of just having invariants or predicates in our world, we now just have invariant names, which are associated to some fixed predicate. And that association is done using saved predicates as an aside to the world. So the world just keeps track of the current state of each of these names, and then we use iris's saved predicates to associate each invariant with its actual predicate. And then for the custom part, it's a bit simpler. We do like other mechanizations of logical relations do and use iris invariants. But additionally, we use these tokens that associate each invariant to the current state in their custom state transition systems. So in this case, we have iris invariants with phi prime, and then we have a token that states which state it is actually in right now. So this is further detailed in the paper, but I still want to highlight one of the main challenges here and why we are not just using iris invariants for both parts of the world. And the problem is, because we want to reason about world bracketed control flow in a language that doesn't, necessarily enforce it, it uses a calling convention to enforce it, we need to distinguish between two kinds of transitions in our state transition systems. And worlds in Irish, which are used for invariants, do not make that distinction. So our W here is a crypty world, but it should not be confused with the worlds with similar crypty logical relations on paper. Our worlds here only contain information about the current state of each invariant, and then we use iris features to actually link the invariants with predicates and associate them to the current state in W. So we're using iris saved predicates to solve to forego solving a recursive domain equation. So although we are still indexed by world W, we still get a, arguably more abstract definition of our logical relation. Okay, so this is done for the aside. Now I want to talk about our main results. So the first main result is the fundamental theorem of logical relations. And in broad strokes, it shows that if a word V has safe authority, then executing V will not exceed the given authority. Concretely, if a word is in the value relation, then it is in the expression relation. And this statement seems quite simple, but we can apply it, for example, to say that an arbitrary list of instruction, so instructions are integers, they're always valid. Let's say we have an arbitrary list of instructions in memory. Any arbitrary list of instruction will always be safe to execute, because any arbitrary list of instruction will always be in the value relation. So any program is safe to execute. And in addition, if we can show that some capabilities within that program that might be there, if it's a closure, if we can show they are also valid, then again, it's in the expression relation. So it's quite powerful. We are able to state that any program is safe to execute, as long as we can show that the capabilities they have access to are valid to begin with. So this is exactly what we need to reason about unknown programs. And we do that in our second main result, which is a proof that a notorious example called the awkward example is actually safe. So here is a high-level implementation of the example. It dynamically allocates some local state, x, and then it calls an unknown function f twice, updating the local state in between the calls. So the assertion that x contains 1 here at the end of our closure relies on two properties. It relies on well-bracketed control flow, right? So we're calling f twice. If one of those calls return at the wrong place, the assertion will fail. And then it also relies on local state encapsulation because, of course, x has to be hidden from f. So we use this example as evidence that our new calling convention enforces these properties. And this is, of course, just a high-level implementation. We want to prove the safety of an implementation in our capability machine. So the first step is really just to translate this to assembly. And with our new calling convention, that gives us around 300 lines of code. With the old calling convention with stack clearing, it's around 400. And of course, since everything is stateful, we also need some kind of knowledge about the initial memory layout, and these details can be found in the paper. So concretely, the theorem we prove is that given any arbitrary function f, or given any arbitrary list of instruction f, the assertion of the awkward example does not fail. So this assertion that x still contains 1 succeeds. And what are some key parts of the proof? So first, okay, there are known parts of the code. We need to step through that using our program logic. So this is sort of the simple part. We just step through instructions. Next, we need to reason about the unknown function f, and for that we use the logical relation. So whenever we hand over control to f, we use the logical relation to reason that indeed it is safe to execute. And then finally, this local state here, since we're never sharing it, we are going to create a custom state transition system that expresses exactly what we need to know. Namely that the local state x goes from 0 to 1, publicly, that it may privately go back from 1 to 0. And we use this custom STS to know for sure that our assertion succeeds. And we can do that because it is never shared. And with all these building blocks in place, we are indeed able to show that the assertion holds. So in this talk, I have presented uninitialized capabilities. I have shown how they can be used as a fast revocation primitive for local capabilities. I've presented an overview of our formalized model of capability safety. And finally, I have sketched out how we verify a classic non-trivial example from the literature. Thank you for watching this video.